All right, team. So this is your final review for physics final exam. I'm not sure how YouTube's going to let me do this, so it's either going to be one really long video or it's going to be um, essentially I'll get as long as I'll do as much video as I can and then upload that. So maybe it's 1, 2, and 3, and then it'll be 4, 5, 6, and then maybe 7, and then 8 and 9, depending on how long everything goes. I seem to remember YouTube has a 10-minute um, upload limit. So we'll see what happens. Hopefully this will help you prepare for tomorrow's final or this week's final. Bear with me as I'm still learning the software and stuff like that. I still can't find a nice little video thing that'll make a little picture of me appear down here like Bozeman does. But so hopefully one day I'll get there. But for now, it's just going to be my voice over it. And I hope it helps. So let me get my pen on here, and here we go. So we're going to start off with number one. A stone is dropped into a deep well and is heard to hit the water 4.83 seconds later. That's important. Determine the depth of the well, and since we're dropping it, we're probably going to assume it's a initial velocity of 0. So what we're going to start with is, as always, this is a one-dimensional kinematic equation because there's no real projectile where it's going across. It's just going straight up and down. We're going to deal with the y dimension. We're going to deal with VI. We're going to deal with VF. We deal with A, T, and D. And we know the VI is 0 meters per second. We would care about the VF if I asked about it, but I don't seem to ask about it here, so we're not going to care about it. The acceleration on something that's being dropped, as we all know, is negative 10 meters per second squared. And the time we know is 4.83 seconds. So going to our list of kinematic equations, we can probably use the D equals VIT plus 1/2 AT squared. And we want to know the D because that's what we're trying to figure out there. Yeah. The initial velocity is 0, so 0t, that's just going to become 0, plus 1/2 negative 10 t squared. T squared. And we know our t, actually put a number in there for it. We know our t is 4.83. So 4.83 seconds squared. And if we do this out on a little calculator, 0.5 times negative 10 times 4.83 squared, you will end up with a distance of negative 116.64 meters, which we're going to say, well, if it's a well, it must be 116.6 meters deep. So you're going to start here at the height of 0, and it's going to drop down. So there you go. Answer number one, 116.6 meters. Hope that helped. We can move right along here and get into number two. The dragster accelerates from rest, so we already know something important. That rest is a VI of 0 to a speed of 186 meters per second. I would say that's going to be a VF over a distance of 398 meters. VI, VF, A, T, D. That distance is 398. Time, acceleration. Oh yeah, I guess I'm going to ask for one of these two. Determine the acceleration of the dragster. So that's the one I care about. That seems to be irrelevant. VF, VI, A, and D. Let's see here. There's got to be an equation that we can use that doesn't have time in it. I'm going to say it's VF squared equals VI squared plus 2AD. So VF is 186 squared equals VI squared, 0 squared plus 2A, 398. And let's see, what can we do here? 186 squared, that is a big number, 34,500 96 equals 2 times 398, 796. So that's going to be 0. So let's see, 796a. So what I do is I multiplied those two together and just brought down the a. So that times that gives us 796 with an a. This is a big number. We're going to have to solve for a. So 34,596 divided by 796 is 43.46 meters per second. So let's get this. A is 46 meters per second squared. As it is an acceleration, that's what we're dealing with. So hope that helped you out. Terminating acceleration to extract or assume uniform acceleration. That seems to be it. So we will move along here, 43 meters per second squared. There's your answer. Third, potato gun launches an apple straight up. So again, we're still dealing with one-dimensional kinematics, and this is actually something I want to make a big deal about here. Note, the acceleration is not 10. An acceleration of 10 or negative 10, as we've been dealing with, is only when you're doing something that has to do with free fall. So a potato gun shooting straight up and something coming straight down, that's free fall. That's when you're going to have acceleration of negative 10. That last example is not free fall. That's uniform acceleration. A car or maybe a sprinter, they're not going to accelerate with the same acceleration that gravity puts on things that are in free fall. This is an example where we're dealing with gravity. So potato gun launches an apple straight up in the air with a hang time of 12 seconds. So that right there is very important. That means 6 seconds up and 6 seconds down. We can use that. How high did the apple go? So now I'm looking for a distance. How fast was it going when it came out of the barrel? So now I'm looking for some sort of a velocity. And when it comes out of the velocity, it's usually a VI. So we can actually look at this 12 seconds and get some good stuff out of it. Let's go with my handy dandy chart, VF, A, T, D. I'm solving for VI, and in this whole trip, I know one thing. I know the velocity, boom, slows down, stops, comes back down. So right here, I know the velocity is 0. I don't know what the velocity down there is, but I know up there it's 0. So if I'm looking for the initial velocity, okay, it shoots, boom, goes up. The final velocity is going to be 0 meters per second. And I know it got there because the acceleration is slowing it down. Gravity is slowing it down by negative 10 meters per second squared. The time that it took to go from the start to the stop was not 12 seconds, it was 6 seconds. So you got to think about this logically. How high did it go in that 6 seconds? That's what we're asking. How fast was it going when it stopped after 6 seconds? That's also what we're asking. So right now we can look at both of these and say, all right, I have two unknowns. I'm probably going to have to use two different equations to get those two unknowns. I have a VF, an A, and a T, and I need a VI. So you know what? We can go with the easy one here. VF equals VI plus AT. 0 equals VI plus negative 10 times 6, because that's our 6 seconds. Last time I checked, VI plus negative 60 equals 0. Add 60 to both sides. We're going to have an initial velocity of 60 meters per second. Boom. And then the question is our distance. All right, so let's see what we can do about our distance. Drag this down a little bit here. Now I have a VI and a VF and an A and a T, and I'm looking for a D. So I can do VF squared equals VI squared plus 2AD. I could do D equals VIT plus 1/2 AT squared. Because I know the time, I might tell you that we could use the D equals VIT plus 1/2 AT squared. So let's go ahead and do that. D equals VIT plus 1/2 AT squared. Our distance is what we're looking for. Our initial velocity was 60 meters per second times our time of 6 seconds plus 1/2 negative 10 t squared. You could do VF squared equals VI squared plus 2AD too. I'm just doing it this way. 60 times 6 is 360. Yeah, I can do math. 60 times 6, yeah, 360. Plus 1/2 negative 10, and our time again is still 6, so 6 squared. So equals 360 plus negative 5 times 6 squared. I just multiplied those two together. Negative 5 times 36, because 6 squared is 36, negative 180. So equals 360 minus 180. And on a good day, that's going to give us 180 meters. Boo. So, to answer your questions here, how fast was it going when it came out of the barrel? 60 meters per second. How high did it go? 180 meters up. Just want to make sure I am recording. Good. That would be terrible if I wasn't. Another one, just like the last one, slightly different information. David Ortiz hits a pop fly straight into the air, assuming the ball goes 65 meters up and back down. So that means 65 meters up, 65 meters down. How much time does the catcher have in time to get under the ball to make the catch? We use our, once again, VI, VF, ATD. Let's see here. We know the distance is 65. We're looking for time. But in order to really do anything, I guess we need the initial velocity. Or we can flip it over on its head. We can treat it as a free fall problem. Instead of looking at the going up, we can look at it coming back down. And we know the initial velocity when something comes back down is 0 meters per second, which fits nicely into all of our kinematics that have 0 as a VI, or just any VI. So 0 meters per second. VF, I don't care about because we're just looking at time. The acceleration is still negative 10 meters per second squared. And what we do is we're going to solve for time. So VI, A, T, and D. That sounds to me like this guy again. D equals VIT plus 1/2 AT squared. But if we're looking at this like a free fall, this is only going to solve half of the time. And we'll get back to that in a second. So our initial velocity, we're going to say at the top is 0. So 0 equals 1/2 negative 10 t squared equals 65 meters. Okay, so at this point, 65 equals negative 5 t squared. And we're going to do a little quick calculation. 65 divided by 5. We're going to end up with a time, time squared, of 13 seconds squared. Don't worry about the units too much. They have come and gone and cancel out and give us seconds squared for time squared. The issue now becomes taking the square root here to get time. So we're going to take the square root of 13. We're going to get 3.6 seconds. Now, we're not done yet. That is for how much of the trip? The going up, the coming down, or the whole thing? You said going down, you're correct, 3.6 seconds. How long did it take to go up? Also, 3.6 seconds. So 3.6 plus 3.6 gives us a total hang time, a total time for the catcher to get under the ball of 7.2 seconds. 3.6 times 2 will give you that. Hope that helped. An object experiences acceleration as it travels in the horizontal direction, assuming no additional force or air resistance. Ladies and gentlemen, we all know that to be false. All right, as it travels in the horizontal, there's nothing helping it, nothing hurting it. That's why you get that nice parabolic shape where the x is constant. The y is always accelerating -10 in projectile motion. That's really important. An object experiences acceleration as it travels in a y. Yep, that's just what I said. There we go. There's our parabola. The x is constant. The y might start out going really fast, but as you get higher, you're accelerating -10, so your velocity gets slower and slower and slower, and then you start falling slower and then a little faster and faster and faster until you hit the ground really hard. So an object experiences acceleration as it travels in the y. That is absolutely true. The acceleration is -10 meters per second every second squared. The acceleration of all objects exerted by planet Earth, at least at its surface, is -10 meters per second squared. The Grand Canyon is 1,600 meters deep. This is another sort of cliff problem. If I were to drop a rock, we're not even doing a projectile two-dimensional. This is still one-dimensional. If I were to drop a rock, how fast is it going to go? You're going to see in a couple of problems like that, we're going to do a throwing problem. But at this point, just a straight up drop. So one dimension, VI, VF, ATD, initial velocity is going to be 0. We're looking for how fast is it going to be going. And we're also looking at how much time will it take. And we're making the assumption, not really making the assumption, it's true, our distance is 1,600 meters. Now this is important. I put a negative there because we're dropping it down. We're not throwing it up. So our displacement, our distance that it's going to be dropping is 1,600 meters. We could solve either of these. We'll take how long will it take, so we can solve for time or we can solve for velocity. In order to solve for either of these, we're going to have to do a little bit of thinking. Which equation can we use? If I use d equals VIT plus 1/2 AT squared, we don't use the final velocity, so I think that's a safe bet to get us our time, but that's going to give us a quadratic. So maybe we should solve for the velocity. And if you guys, d equals VIT plus 1/2 AT squared. I don't know that t and I don't know that t. And because one's t and t squared and we have an addition sign in the middle, we're going to have to use the quadratic formula. Not that that's hard, but there is an easier way to do it. And that easier way to do it is to solve the final velocity first. So what we will do is do VF squared equals VI squared plus 2AD. Our final velocity is what we're looking for. 0, that couldn't be easier, plus 2, -10, 1,600. Zeros always look like 2's. Apologize for that. So VF squared equals, let's see here, 2 times -10 times 1,600. It's going to be -32,000 meters squared per second squared. And again, that's all the algebra up there with the units, which I'm skipping over. Square root, square root. Now you're taking the square root of a negative number. That's a big time no-no. But because we're dealing with a vector, we're just saying that this 32,000 is a negative direction, which means we're dealing with something going down. So we can kind of ignore that negative and then plug it back in. Square root of 32,000. Square root of 32,000 is 178. VF equals 178 meters per second, but because we're dealing with a vector quantity, it's actually negative 178 meters per second. That just means it's going down. The other thing, we can do time. Well, how long does it take to go from 0 to negative 178 with an acceleration negative 10? That's not terribly hard. Vf equals Vi plus At. Solve for the time. Negative 178 equals 0 plus negative 10t. So we're dealing with a time of, the negatives cancel out. We will be dealing with a time of, divide 178 by 10, 17.8 seconds. Fair enough? Keep going here. I've always wanted to go bungee jumping out of an air balloon. I jump out of the balloon with 300 meters of rope tied to my feet. Do I have enough rope to free fall for 6.5 seconds? There are two ways you can do this. One of them is to figure out how long so how much time will 300 meters of rope buy me? The other way to do it is how much rope for 6.5 seconds of free fall. I can do both here. All right, so we're going to do VI, VF. You're going to see this is very similar. ATD. VI, VF, ATD. In both of these, the initial velocity, because we're bungee jumping, is 0. In both of these, the acceleration is negative 10. This is the difference. We're going to use 6.5 seconds here and solve for distance. If that distance is bigger than 300 meters of rope, that means one thing. If that distance is smaller than 300 meters of rope, that's another thing. Here, we're going to use the 300 meters of rope, and we're going to solve for the time. So let's go, and if it's less than 6.5 seconds, that means one thing. If it's more than 6.5 seconds, that means something else. So we will do here, we're going to solve for d. So d equals VIT plus 1/2 AT squared. D equals 0. VIT is going to be 0 plus 1/2 negative 10 t squared, and that t is 6.5. So I'm actually going to go back. I'm going to get rid of this and plug in 6.5 squared. That decimal place back there. All right, so our distance is 1/2 0.5 times negative 10 times 6.5 squared. And you're going to end up with a distance of 211.25 meters. So, in order to drop for 6.5 seconds, I need 211 meters of rope. How much do I have? 300. Do I have more than I need? Yes. In fact, I will fall for longer than 6.5 seconds. Coming over to do it the other way. Let's see, VI, A, and D, and I'm looking for time, so let's see, I can probably do that thing again. D equals VIT plus 1/2 AT squared. I'm not so concerned about the quadratic this time because I know my distance is 300. The VIT, the VI is 0. Time, that's going to be 0. Plus 1/2 negative 10 t squared. This time we're solving for that time. So I got 300 meters rope. How long am I going to free fall for? Let's find out. 300 meters equals negative 5t squared. I just 1/2 negative 10 brought down the t squared. Let's see, 300 divided by negative 5. And actually, shame on me because I'm dropping. That's a negative, that's a negative, that's a negative. So is that for what it's worth. So negative 300 divided by negative 5 equals 60. 60 is t squared. We don't want t squared, we want t. So our time is going to be the square root of 60. 60. And that is going to give us 7.74 seconds, which, if I wanted to jump out and fall for at least 6.5 seconds, I have more than I have about 1 3/4 seconds more free fall than I was hoping for. Bonus. Hope that helped. We are about 1/4 of the way through, so this is good stuff. 10. If Michael Jordan has a vertical leap of 1.29 meters, calculate his takeoff time and hang time, or calculate his takeoff speed and hang time. All right. Not terrible, but this has been one that has given you so many issues. So, let's draw a picture. Here's MJ. He jumps up 1.29 meters, and then he falls back down 1.29 meters. Let's make our chart. EI, EF, A, T, D. And we are looking for his takeoff speed and his hang time. So we're looking for time. We are looking for initial velocity. So, sorry, I had to take a quick break. If Michael Jordan has a leap, so here's what we got. We're looking for the initial, looking for the time. We know one thing. Up here, when he comes up, our velocity is 0. We know the acceleration is negative 10 meters per second squared. All right, so here's what we can do. VI, VF, A, and we have a D of 1.29 meters. So I'm wondering if we can do D equals VI T plus 1 half A T squared. 1.29 positive, he's jumping up, equals, I don't know, plus 1 half A T squared. That's too many things I don't know, because I don't know what VI and I don't know what T. So this is no good. Or is it? Instead of looking at this going up, what if we looked at it coming down? Let's just say for a minute his initial velocity is 0. And we don't know his final velocity. And why is that good for us? Well, if we solve for his final, it's the same. If we solve for his final down here, it's the same as the initial that he jumped up with. So the final velocity is what we can solve for. And the initial would be 0 times t plus 1 half a t squared. But we know the a. I'll go back and explain this again as soon as I get everything written down. 1 half negative 10 t squared. Instead of looking at going up, if we look at it coming down, we know the same distance, except this time it's a negative 1.29. All right? And all the stuff that's going on here and here is the same. It's just that the signs are different. So let's play this out. Let's solve for time first, and then we can go back and deal with some velocities. Negative 1.29 equals negative 5t squared. So let's divide negative 1.29 divided by negative 5. We'll end up with a t squared of 0.258 seconds squared. Square root of that, square root of that, t is 0.507 seconds. just confirm that. Answer. Yeah, 0.508, 0.507, whatever. So that's 0.507 for the going down, the half a trip. The going up is the same thing, 0.507. So we know the total time is going to be 0.507 times 2, which is going to be about 1.01 seconds. So there's his hang time. Hope you followed that. What was his takeoff speed? Well, that's pretty easy too, because you can treat it as a free fall, and you can figure out his final velocity. So VF squared equals VI squared plus 2AD. We're looking for his final because that's what he's hitting the ground with. We know the distance is negative 1.29 meters. So VF squared equals VI squared, which he was starting up here, is 0, plus 2, negative 10, negative 1.29. Negative 10 times negative 1.29. Why am I doing this in a calculator? VF squared. VF squared equals 12.99 meters squared per second squared. Take the square root of both sides. That you need a calculator for. 3.5 VF. It's going to be 3.59 meters per second. So that's how hard he hits the ground when he lands, which is also how hard he jumps up when he jumps. So, what's his takeoff speed? 3.59 meters per second. What's his hang time? 1.01 seconds. And the trick to this whole problem is you guys have had a little bit of issue with in class and going back to even when you took this exam. You have to break it in half and kind of flip it on its head. You don't have enough to just play with what he's doing when he goes up, but you have plenty to deal with when he's going down, all right? And that is almost the end of our one-dimensional kinematic equations, okay? Plane has a takeoff speed of 88.3 meters per second, requires 1,365 meters to reach that speed. Determine the acceleration of the plane. Not terrible. VI, VF, ATD. Plane has a takeoff speed of 88.3 meters per second. How long does it take to reach the takeoff speed? Okay, so we know that's the VF, 88.3. Last time I checked for initial velocity, you're not getting on the plane while it's moving. I'm going to say the initial velocity is 0. Acceleration is what we're looking for. Time is also what we're looking for. The distance is 1365. That's actually the distance of the runway at loading. So a little bit of research for you. Determine the acceleration and the time. How can we do this? We do the time first. No, we can do the acceleration first. Or can we do either first? VF equals VI plus AT. Can't use that because we don't have T or A. VF squared, how's this one? Equals VI squared plus 2AD. How's that? 88.3 squared equals 0 squared. That makes life easy. Plus 2A, 1365. I think I can figure out the A from there. So let's do some plug and chug. 88.3 squared. It's a big number, 7796. Equals 2 times 1365. 2 times 1365. 2730. A. So again, multiply those two, brought down the A. Divide both sides by 2730. That goes away. A is going to be 730. Should give you 2.85 meters per second. Fair deal. So that's my A. And our time, we can go back to the old VF equals, sorry, my voice says one thing, the pen does something else. VF equals VI plus AT. So VF 88.3 equals 0 plus 2.85 T. Solve for T. So divide both sides by 2.85. That's irrelevant. Divide that side by 2.85. T is going to be 3 divided by 2.85. 31, call it 30.98, but 31 seconds. There you go. So that's your time, that's your acceleration, and that's the end of the kinematic section. I would also go back and look at two-dimensional kinematics. I seem to have not thrown one in here, but I don't know, just go ahead and remember that our two-dimensional stuff, we got our clip problems that we have a couple of videos on. We also have some launching stuff. You might need to find the distance as well as the maximum height. And there will be one or two in there, but I believe I'm giving you options on which ones you do. So hope this helps. Now we move on to force. These are more a Sudoku issue. All right, so an applied force of 50 newtons. So there it is used to accelerate an object to the right across a surface that has friction. The object encounters 10 newtons of that friction. Use this diagram to determine the normal force, net force, mass, and acceleration. First and foremost, I know if gravity is pushing it or pulling it down with 80 newtons and it's on the surface, I hope it's not falling through the surface. The surface is exercising a normal force of also 80 newtons. I know that the mass can be gotten from the weight force, which is also known as the gravitational force, which is 80 newtons. If you remember, 80 newtons equals mg. You know g is 10, so 80 equals m times 10, which means that m is 8. Divide both sides by 10. The F net, I know the F net is the addition of all the different forces acting on this box. So I know 80 up and 80 down, those two cancel because force is a vector. This is actually a negative 80. So you add the 80 and the negative 80, you get 0. You get 50 to the right, 10 to the left. That's actually a negative 10 because it's going to the left. So 50 minus 10 is 40. So that's the net force. And on a good day, as my t-shirt says, F net equals MA. So 40 newtons equals the mass, 8 times A, which is what we're trying to solve for there. 40 divided by 8 on a good day is 5 meters per second squared. Hope that helped. Using the same basic dialogue, we can do the same basic thing here, except this time we have to solve for the force of friction. And we have to solve for the force of gravity. We have to solve for the normal force. And all we know is that we have a 5 kilogram mass. So let's play the game here. My mass is 5 kilograms. What do we got? We can figure out the weight force, or the force of gravity, by doing 5 kigs times gravity, which is 10. but whatever. So FG is negative 50 newtons. And it makes sense because it's negative because it's a vector going down. It's sitting on a table, so my normal force had better be what? I hope you said positive 50 newtons. Okay, so if I know my normal is 50, my gravity is 50, cool, it's not going through the table. The next piece we could do is figure out the friction. FF equals mu Fn, and I know my Fn is 50. My mu is 0.1. 0.1 times 50 is a frictional force of 5 newtons. Now I hope you realize that there is only one force acting in the x dimension here. That's huge because it means that the box is slowing down. So we should end up, first and foremost, with a force going to the left being a vector. We're going to have a negative. And the bigger deal is the acceleration is going to be negative now because it's accelerating to the left because friction is the only force working on it. The normal and the gravity cancel out, so our net force in the y dimension is going to be 0. Acceleration on a good day, according to my shirt, F net equals ma. F net is frictional force, so negative 5 equals m, which is 5 times my acceleration, which is what we're looking for. Negative 5 divided by 5 is negative 1. And let's see here. 50 and 50 cancel out. The net force is going to be negative 5. That's why I use those. So I hope this one makes sense. Brian is walking through school cafeteria. These will actually go pretty quick, but does not realize that the person in front of him just dropped his carton of chocolate milk. Oh no. Brian, who has a weight of 420 newtons. Let's draw Brian. He's got a weight of 420, which means he's got a normal force also of 420. So equals Fn equals Fg, or weight force. Jumps on the Miller coefficient. Sliding friction between him and the floor is 0.04. What's the sliding friction? So we're looking for F, and we are dealing with mu times normal force. I give you a mu of 0.04. And the normal force we figured out because we know its weight force is 420. 0.04 times 420 should be 16.8 newtons. That's all the force that this poor kid has holding him on the floor, preventing him from slipping. 16.8 newtons. Okay, continuing. While redecorating our apartment, Kitty slowly pushes an 82-kilogram china cabinet across the floor, which resists the force of friction with a force of friction of 320 newtons. Basically, calculate mu. So again, here's this thing. Kitty's pushing it. It has a mass of 82 kilograms, which means it has an Fg of 820. Again, voice says one thing, pen does another. 820. And if we know the gravitational force is 820, we know the normal force is going to also be 820, unless it's going through the floor. You could say it's negative, but that's kind of not what the question's asking. So while redecorating her apartment, she pushes this thing and it resists with a frictional force of 320. So we know the FF is 320. We know the Fn is 820. And we don't know the mu, but we want to know the mu. And we know that FF equals mu Fn. And on a good day, you can plug stuff in. 320 equals mu times 820. Calculate mu. Algebra here. 320 divided by 820 should give you a mu of about 0.39. And there are no units on mu. Don't forget that. So I hope that helped. 70 kilograms, St. Bernard goes out the back door, but the dog refuses to walk. Coefficient of sliding friction between the dog and the floor is 0.5. How hard must Skye push the dog in order to move the dog with a constant speed? That's really, really important. The fact that it's a constant speed, that means there is no F net. So she's not pushing harder one way and the dog's pushing not as hard the other way. Everybody's pushing exactly even. That's why we're saying so no acceleration, so the push force equals the frictional force. So what we're really saying is, here's the dog, big dog, small dog, ugly dog. The dog's got a gravitational force, Fg, of 700 because 70 kilograms times gravity. Dog also has an F net, normal force of 700, and mu is 0.5. So if she's going to be dealing with this, we have to overcome friction, which is mu times the normal force. So the frictional force is going to equal 0.5 times 700, which is 350. Again, that equals the frictional force. If we don't want it to accelerate, that friction has to be exactly equal to the push. So she has to push with 350 newtons. The dog is going to resist with 350 newtons, and there will be no acceleration, so the dog will just kind of coast along. Hope that helps. So push equals 350 newtons. All right, here we get into some more complicated and fun problems. Deer jumps in front of my car as I'm traveling 25 meters per second. This is going to be a lot of everything. We'll start out with a VI, VF, A, T, D. VI, we're starting out 25 meters per second. Jam on my brakes and lock them. The U between the tires and the ground is 3.6. My car has a mass of 1,250 kilograms, and there's 50 meters between my car and the deer. Will I or will I not hit the deer? I hope that my velocity final is going to be 0. I don't know my acceleration, but I know I have 50 meters between me and the deer. Don't fall in the trap of putting 50 here. The fact of the matter is, 50 meters is what you're shooting for. It's not what you're solving for, and that will become evident in a second. I need to find the acceleration, and the only tie that binds acceleration in kinematics and the only tie that binds kinematics to dynamics is acceleration. And if you remember, F net equals ma in dynamics, you can solve that acceleration and throw it in there. The trick here is you got to realize that the F net is the force of friction. The car isn't going through the ground, the car isn't flying away from the ground, the car is simply stopping. And the net force that's making it stop is caused by friction. So what we start by doing is solving for what friction is. FF equals mu, which is 3.6 times the normal force. My mass, so here's my car. Fg is 1250 times 10, 12,500. My normal force is also 12,500 newtons. So force of friction, U times the normal force, 12,500. So what we can do is figure out very quickly 12,500 times 3.6 gives us 45,000 newtons of stopping power. Your tires, my tires, these tires will give us 45,000 newtons of friction. This is kind of important. 45,000 newtons equals MA. Because we're also dealing with F net, which equals MA. 45,000 newtons equals 4,500 kilograms times the acceleration. So our acceleration is going to be 10 meters per second squared. Going through, 6 times 12, yeah, okay, 45,000 meters, so that's a happy coincidence that you get 10. Also, it's friction, so we're dealing with a negative, so that's going to be a negative, which means that acceleration is a negative 10 meters per second squared. And going back, and geez, we got acceleration coming out of here, and now we can throw it into here and just do a kinematic. D equals VIT plus, that's not really going to help us because I don't have time. BF squared equals VI squared plus 2AD. So I hope that I'm stopping 0. How long does it take? 25 squared equals 2, negative 10. Solve for D. Equals 625 plus negative 20 D. 625 divided by 20. 31 1/4. So, well, getting there too fast. So subtracting 625 from both sides. Negative 625 equals negative 20b. Divide both sides by 20. Divided by negative 20. Your distance is going to equal 31 1/4. Now, the deer is 50 meters away. I stop in 31 1/4 meters. So here's Bambi. Bad Bambi. Yeah, let's just go with it. So here's my car. I stop here, 31 1/4 meters away. Bambi is 50 meters away. I don't even come close to her. So, hooray. Everybody wins. Next problem, I love shuffleboard. Length from the release at 10 points is 33 1/3 meters. Mu is 0.3 for the 0.3 kilogram puck. Well, that makes no sense. Maybe I should make the grammar better. I love shuffleboard. Length from the release to 10 points is 33 1/3 meters. Mu is 0.03 for the puck and the court, right? That makes sense. With what speed must I release this thing? So I don't know if any of you know what shuffleboard is, but it's a very simple game. You take a puck and you slide it 33 meters away, and each of these little boxes is points. What you want to do is slide it until it gets to either the 10 points or 5 points or whatever. So it's a fun game. What we're going to be doing is basically the same thing one more time. We're going to be marrying kinematics, BI, BF, ATD, with dynamics. So we know this time that we're aiming for 33 1/3 meters. So we can use that, 33 1/3 meters. We're going to have to solve for the acceleration again. The VI is also actually what we're solving for. And the VF has got to be 0 because we want the puck to stop. We know that mu is 0.3 and the mass is 0.3 kilograms. which means the gravitational force, the weight force, is 0.3 times 3, times 10. So our weight force is going to be 3 newtons. Now every puck has 3 newtons go down, which means it also has a normal force of 3 newtons going up. Hope that makes sense. So the question is, how much friction can we generate from the puck? Ff equals mu times normal force, which is 0.3 times 3. And a third of 3 is 0.99, 9999. 0.3 times 3, 0.9. So the force of friction is 0.9 newtons. And if we remember correctly, 0.9 newtons equals my net force 2 equals ma equals 0.3. So 0.9 divided by 0.3 gives me 3 meters per second. There's friction, so we're dealing with a negative. We're slowing it down, negative 3 meters per second. The reason that we do this is because the force of friction is the net force. So you release the puck, and it just slides, slows down. It's kind of like curling, except there's no ice in the Winter Olympics. So you slide it, slow it down, and hopefully it lands right where you want it to. So the net force is ma, and that's why you figure out the friction first equals ma. My acceleration is negative 3 meters per second. Okay. How hard do I have to shoot it to have this all work out? Well, Bf squared equals Bi squared plus 2ab. Bf squared I'm hoping is going to be 0. Bi squared is what I'm looking for. 2 times negative 3 times 33 and a third. So 2 times negative 3 times 33 and a third. Zero equals Bi squared plus negative 19.8. Add 19.8 to both sides. Bi squared, square root of 19.8. Your initial velocity should be 4.4 meters, 4.45 meters per second. These are tough ones. These are good ones. These are understanding that you're dealing with friction, which is the net force, which equals ma, which you can then go back and plug into the A here and do some kinematics with it. So these are good problems. I would really know about these. And hopefully this one is going to be our last one like that. Yep. Now we start in with centripetal motion. Okay. So final velocity of a bowling ball that's doing stuff. So we start out with, again, our VI, VF, ATD. Let's find velocity of a bowling ball that has a mass of 7 kgs, which means it has a weight of 70 newtons, which means it has a normal force of 70 newtons. I just kind of do all this stuff in the beginning without even reading the rest of it, because I'm assuming I'm going to need it. After it's traveled 30 meters down the bowling alley, it's thrown with a velocity of 17 meters per second, and we're looking for the final velocity. And mu is 0.03, so we're going to slow it down, which I remember vividly on the test. None of you guys realize this. The friction is the net force, which equals ma, which we're going to plug over there. Ff is mu times the normal force, which equals 0.03 times 70. So on a good day, frictional force 0.03 times 70 is 2.1. 2.1 newtons. That's my frictional force. 2.1 newtons equals my MA, because F net equals MA, and the only thing holding the ball, slowing it down, changing the speed is friction. The bowling ball has a mass of 7, so 2.1 equals 7A, which means the acceleration is 0.3. 2.1 divided by, I just want to make sure that this is right, 0.3. 0.3. Now, here's where you guys screwed up in the exam. This is friction. 0.3 meters per second squared, slowing down. So again, the acceleration is negative 0.3 meters per second squared. We're looking for a final velocity, so Vf squared equals Vi squared plus 2AB. 17 squared plus 2 times negative 0.3 times 30. 17 squared, 289, plus negative 0.6 times 30. What's negative 0.6 times 30? Negative 0.6 times 30. Negative 18. So 289 minus 18. 271. Vf squared, so all the way down. Vf squared equals 271. Take the square root. Take the square root. So Vf will equal 16.46 meters per second. This is the beauty of physics. If you know a little bit about a bowling ball, you can figure out how fast it's going to be going when it hits the pins. All right. Hope you understand this whole forces thing. That's kind of a chunk of the final exam. Now we go into some triple motion. This first piece is acceleration, triple acceleration here. Airplane traveling twice the speed of sound, which is 688 meters per second. Pulls out of a dive by moving in an arc of 6.3 kilometers. What's the acceleration in G's, and does the pilot pass out? Remember, 4 G's is the limit of force before you pass out. And remember, 1 G is 10 meters per second squared, which is all fine and good. So triple acceleration, which is what we're figuring out, equals V squared over R, which is 688 over R, 6,300 meters. Remember, this has to be meters and meters, not kilometers. So you got to change that, multiply by 1,000 to get kilometers back into meters. So 688 divided by 6,300 is going to give us 0.109 meters per second squared. Which is way less than 1G, because 1G is 10. That's 0.1, so this pilot's definitely not going to pass out. Roller coaster moves. This is going to be a little tighter here. 65. We're looking at the acceleration again. So, oh, V squared. That's why that was so low. we've squared that, which means this is all incorrect. Might be. So, you gotta square that. That's why. That's really low. So let's try this again. 688 squared divided by 6,300. There you go. 75.13 meters per second squared, which divided by 10 meters per second squared is 7.5 Gs, which means a pilot passes out. So again, centripetal acceleration, b squared over r. AC equals b squared over r. 65 squared over 39 is going to give us some interesting stuff for a roller coaster. A little bit of whiplash. We'll see. 39. Yeah, 10 Gs. It's not terrible. You won't like that very much. So 108 meters per second squared, which if you care is about 10 Gs. You would go to sleep too. All right, so now child on a merry-go-round is going around with a speed of 4.5 meters per second, 3.3 meters from the center. Calculate the centripetal acceleration of the child. That's easy. We can always, that's not going to be deadly. The second part of this is going to be a little bit interesting. So first off, AC equals v squared over r. 4.5 meters per second all squared over 3.3 meters, which means, let's see, 4.5 squared over 3.3. So 6 meters per second squared, 0.6 Gs. I'm sorry, 6.13 meters per second squared. Cool. So there's the centripetal acceleration. Check. Assuming the child has shoes with friction at 1.9 with what speed will she have to move in order to slip off? So now we're going to say FF is giving us the centripetal force. So let's stick in algebraic terms here. Mu Fn is given to us, is giving us mv squared over r. FC, centripetal force, mv squared over r. I hope you have your equation sheet and you see that. Fn is m equal to mg. So we can really say mu mg equals mv squared over r. The m's will cancel. Mu times g equals v squared over r. Now, the merry-go-round and the friction and gravity are all given. So we're just solving for the velocity. So the radius is 3.3 meters. The speed is irrelevant because we are going to solve for that. And mu is 1.9. So mu 1.9 times 10 for g equals v squared over, what was my radius? 3.3 meters. So 19 equals v squared over 3.3. Multiply both sides by 3.3. We're looking at v squared equals 62.7. Square root, 7.8. V is 7.91 meters per second. And the question really is, and I can go back and explain this a little bit more now. So 7.9 meters per second. When the kid's not holding on, and the shoes are thrown in there. So the kid's feet, here's the merry-go-round, and the kid's on the merry-go-round, and her shoes are the only thing that are in contact. The kid's going to go around in circles, trying to go off tangentially at any given point. And the shoes are the only things that are giving us friction, and that friction is what's going to make her go in a circle. So that FF equals FC. The big deal is at what point, and we all know this, at what point does friction let go? And you can look at it with car tires, you can look at it with a lot of things. So this is actually a really important concept. FF equaling FC, and you can figure out at what point you have more need for centripetal force than friction that you have. All right, and we've done a bunch of these, and I hope that you still have notes on them. You should probably look at them. But this is how you attack that kind of a problem. You simply set FF equal to FC. Okay. So one part you are solving using my speed, my velocity. The second part, you're creating your own velocity. This is another problem just like that, except now we're dealing with tensile strength. So how much can string handle? We're still dealing with circles, centripetal force, but now we're dealing with tension strength. So according to tensile strength of 75 newtons, how fast can a 2.5 kilogram lead weight be spun without breaking the cord at 1 meter, 1.5 meters, and 2.5 meters? So our tension at maximum is 75 newtons. So we're going to leave that as is. So 75 newtons equals that tension is giving our weight the ability to go around in circles, all right? And 75 newtons. Okay. How fast? So mv squared over r. Our m is 2.5 kilograms. V squared over r. So for our first little piece, 1 meter. For our second little piece, do the same thing. 75 newtons equals 2.5 v squared over, not 1 meter, 1.5 meters. And then 75 newtons equals 2.5 v squared over 2.5 meters. So we can do this easy enough. Handy dandy calculator. 75 times 1 divided by 2.5. Then we take the square root of it. 75 times 1 divided by 2.5. And we take the square root of it. I'm abbreviating the algebra, trying to save you guys some time because this has been going for like more than an hour. 5.4 meters per second. 5.47 meters per second. That's the D for that. Holding everything equal, 75 times 1.5 divided by 2.5, square root of that, 6.7 meters per second. And then 75 times 2.5 divided by 2.5, square root of that, 8.6 meters per second. There? There. Another one where we have a centripetal problem coming out of friction. So generally, so we're dealing with one more time FF equals FC. General elevating, cleaves dipping along 50 meters per second, goes around a bend with 75 meters. Will it slide off with frictional tires, and at what radius will the car slide off? All right, so first deal. FF equals mu Fn, which is mu mg. See, I'm going to save this. Equals FC, and FC is mv squared over r. Masses cancel, so I don't care how heavy the general E is. Mu, according to this, is 1.8 times 10, which is g, is v squared, 50 meters per second, squared over r, which is 75. You might say, but wait, there's nothing to solve for. Well, you're looking at, is this friction bigger or smaller than the centripetal stuff needed to keep it on the road? Now, I could also throw the 1,500 kilograms. So is there more friction than centripetal force? But we know, through what we've done this year, that the masses will cancel. So basically, if this side is bigger than this side, the tires can handle it. If this side is bigger than this side, you need more centripetal acceleration than the tires can give you. So let's see. 1.8 times 10, 18. Is that equal to less than or greater than 50 over 75? 50 squared over 75. Squared over 75, 33 1/3. So I need 33 1/3 meters per second squared to do my acceleration around that. My tires can give me 18 meters per second squared. So guess what, kiddies? The tires will not give you that acceleration, and you will go flying off. The next question we're asking is, at what radius will it start to slide off? So we know it's doing it here. How big does the radius have to be in order for it to maybe not slide off? We can do the same thing. Ug equals v squared over r. And this time it really is an equality. U times g, same tires, same gravity. 18 equals same speed, 50 squared, but now we're looking at it over what radius? So 18r equals 50 squared. Solve for r. So 50 squared divided by 18, that radius has to be 138.8 meters around, or in radius, in order for that car to not slide off with those tires on planet Earth with our gravity. Okay? And again, you could do this all by throwing the masses back in. The numbers will just get bigger, but the basic principle is the same. All right, 25. What's the maximum speed you travel in a typical car on a dry day when going around a curve of 75 meters? Assume the friction is 2.1. How about a rainy day when it drops to 1.2? So we'll do this twice. Dry, rain. So again, typical, and I'll do it out the long way. So instead of doing it like we did with 24, I'll do, let's see, FF is going to be my centripetal force. So mu times m times g equals mv squared over r. And we're solving for the maximum speed. So my mu on a dry day is 2.1 times 1,000 times 10. Where does that equal? 1,000 v squared over 75. 2.1 times 1,000 times 10 divided by 75. I'll look at that in a second. So 2.1 times 1,000 times 10, 21,000 equals 1,000 v squared over 75. So we're going to multiply 21,000 times 75, then divide it by 1,000. So multiply both sides by 75, then divided it by 1,000. So I've got v squared equals 1575. Because I'm at the bottom of the page, I'm just going to divide everything, or take the square root of 1575. So you should get a velocity of 39.68 meters per second. Now, when it rains, I'm going to save myself some headache here. Again, FF is FC. The thing making you go around in circles is frictional force. FC. And again, mu mg equals mv squared over r, but now I'm going to save the headache. Get rid of the m's. Mu is, on a rainy day, 1.2, not 2.1. Equals v squared over r. And the r is still 75. So 1.2 times 10 times 75. 1.2 times 10, multiply that by 75 to get rid of it. We're going to have 900 equals v squared, square root, square root, square root of 900. It's 30 meters per second. Easy. A little bit more difficult just because the numbers are bigger, but you can see we cancel out the masses. We didn't cancel out the masses. It's the same thing. On a dry day, about 40 meters per second. On a rainy day, about 30 meters per second. Force of 350. This is going to turn us into a projectile problem. So this is going to be actually a pretty good one. Because I said before, I didn't throw a true projectile in here. This is a marriage of projectile and centrifugal force. This is like a really big, nasty, good question. A force of 350 newtons is exerted on a 2.5 kilogram discus as it's rotated in a horizontal circle at arm's length of 1 meter. Calculate the speed of the discus. That's not hard. The force is 350, so we know it's going around in circles. And we know the equation is mv squared over r. And I have an m, and I have an r, and I have an fc. So 350 equals 2.5 v squared over 1 meter. Boom, boom, boom. 350 times 1 is 350 divided by 2.5. 350 divided by 2.5 equals that. 140. So 140 equals v squared. Take the square root of 140. You should get a velocity of 11.83 meters per second. Now, so that's what's going around. It's going around and around and around and around. Finally, we release it around and around and around, and then it releases at an angle of 45 degrees. How far does it go? This is a cool question because now I have a velocity. VI, VF, A, T, D. Ah, this guy is bringing back stupid kinematics. Not only is it stupid kinematics, but it's now X and Y kinematics because 11.83 meters per second at an angle of 45 degrees. Now I need to know this stuff. So we're going to have to make sure that our calculators are in degree mode. We'll do that right now. Okay. And we need to know the initial velocity in both the x and the y. And I'm happy that this is here because we can refresh ourselves on this. 11.83 to get the x, 11.83 cosine 45 and this will be 11.83 sine 45. Okay, so this is also Katoa stuff. 11.83 cosine 45. It's 8.36 meters per second. I'm going to verify this, but 11.83 sine 45 is also 8.36 meters per second. How far away is it going to travel? So we're looking at distance in the x. So I'm not worried about the y. Remember, in two-dimensional projectile motion, the only thing that's accelerating is the y, negative 10. This is 0, which means if I start at 8.36, it's going to end at 8.36. This guy, 8.36, if I'm going up 8.36, at the end of it, I'm coming down with 8.36. Okay. Time, that's what we care about. So I would say VF equals VI plus AT. This is all in the y dimension. So negative 8.36 equals 8.36 plus negative 10t. So now you have to take negative 8.36 and subtract 8.36. Why? Because this minus that is going to give us negative 10t. So negative 16.72 equals negative 10t. Divide both sides by negative 10. 1.672 equals time. 1.672. 1.672. So now I can do d in the x equals bit plus 1/2 at squared, all in the x. Dx equals, that's going to be 0 because my acceleration in the x is 0. Bit, so 8.36 times 1.672. Let's do that out. 1.672 times 8.36. 13.4 meters. 13.997 meters. So, not bad. This is a good question because it relates, again, two-dimensional projectile motion with your angles and all that good stuff back to centripetal force and acceleration and centripetal velocity and stuff. So, very, very good problem. Definitely an A problem. Projectile, centripetal. Next up, we're going to be dealing with sort of your lab from a few months ago, feeding the string through the straw. We got this thing going around like that. We know it's 1 kilogram there, tied to the end of the rope that is spun through a straw and tied to an unknown mass on the bottom, question mark. The mass is being spun at a speed of 3 meters per second with an R of 1.1. What's the weight? Okay. So we know FC, which in this case is actually supplied by this guy, equals mv squared over r. So FC equals, the mass is 1 kilogram. V squared, 3 meters per second, squared over 1.1. This is probably the easiest question on the entire thing. Just plug and chug. 1 times 3 squared divided by 1.1. 8.18 newtons. So the unknown mass has a weight of 8.18 newtons. Calculate g at the surface Jupiter. So we're going to do little g. So now we're getting into gravity. This is going to be quick plug and chug stuff. Little g at the surface Jupiter. The mass is 1.9 times 10 to the 27 kilograms, and its r is 69,911 kilometers. Little g equals big G mass of the planet over r squared, which is 6.67 times 10 to the negative 11 times 1.9 times 10 to the 27th, all over the radius, 69,911 kilometers. We need it in meters. And then you're going to have to do some parentheses and stuff like that. So 6.67 times 10 to the negative 11 times 1.9 times 10 to the 27th divided by some parentheses here, 69,911 000 squared, close my parentheses, 25.92 meters per second squared. At the surface of Jupiter. Next, calculate the force of attraction between you and your best friend standing 8 meters away. If you have a mass of 60 and you're, so we're dealing with force of attraction, which is now Fg equals big G m1 m2 over r squared. There's actually a pretty good video about this too, up on the web, up on YouTube. 6.67 times 10 to the negative 11 times u times your friend, masses, kilograms, all over the radius, squared. So this should be a very small number. 6.67 times 10 to the negative 11 times u, 60, times your friend, 80, divided by 64, 4.7 times 10 to the negative 9 newtons. How fast do you accelerate towards your friend if you were in space? Well, little g equals big G mass of the thing doing the pulling over r squared. How fast do you accelerate towards your friend? Well, your friend's doing the pulling and they have a mass of 80 kilograms because that's what we said in that problem. So little g equals 6.67 times 10 to the negative 11 times 80 all over 64, because that's, again, the radius, the distance between us, the 8 squared. That's going to be a pretty small number too. 6.67 times 10 to the negative 11 times 80 divided by 64. 8.3 times 10 to the negative 11. Let's try that again. 8.3 times 10 to the negative 11. Just want to make sure of one thing. This 6.67 times 10 to the negative 11 times 60. Yep, that's all good. Okay, so I'll put a circle around this guy. Calculate the orbital velocity of a satellite orbiting 120,000 meters above the Earth, the surface of the Earth. If the Earth has a mass of 6 times 10 to the 24 kilograms and a radius of 6,300,000 meters. Okay, so now we're doing velocity of orbit. And if you remember how we got that, that was all based on FC coming from FG. Now, FC is mv squared over r, and FG is big G m of the object, mass of the planet, over r squared. This is also mass of the object because it's the mass of the thing going in circles. The mass of the objects cancel out. So v squared over r equals big G mass of the planet over r squared. If I want to get rid of this r, I would multiply it by r, cancel, cancel. That goes away. So we end up with the equation v squared for orbital velocity equals big G mass of the planet over r. Or orbital velocity equals the square root of big G mass of the planet over r. I would know how to do this. I'm not going to give it to you, and I don't think I had you write it down because I want you to be able to think about this one. So it turns into a simple plug and chug, but getting there is a little difficult. 6.67 times 10 to the negative 11th times the mass of the planet, 6 times 10 to the 24th, all over 6300000. 6,300,000. Take the square root of that whole thing. So, but you can't just be that simple because you have to add another 120,000 meters above it. Because I tell you, it's above the surface, and that's the surface. So, let's plug all this in. 120, 123, 120,000 meters plus 6,300,000 meters. This whole thing here is going to become 642, 1, 2, 3, 4. So now we can actually do the plug and chug. 6.67 times 10 to the negative 11 times the mass of the Earth, which is 6 times 10 to the 24th, divided by 642, 0, 0, 0, 0. And then we take the square root of that whole thing. 7,000, oh boy. V will equal 7,895 meters per second. Student with the mass, now we're into energy. Student with a mass of 80 kgs runs up 3 flights of stairs in 12 seconds. Student has gone 8 meters. Determine the amount of work. Work equals force times distance, or mgh. I'll just take mgh. The work is 80 times 10 times 8. So the work is 6,400 joules. Note, we don't use that because time is power. We're doing chin-ups. We lift 0.25 meters in 2 seconds. What's the power? Power is work over time. Work is mgh in this instance over time, which is 42 times 0.25 times 10 for g over 2. So let's do that out. 42 times 0.25 times 10 divided by 2. 52.5 watts. I hope I remember that's joules. So 52.5 watts for that. Next, cart's loaded with a brick and pulled at a constant speed along an inclined plane at the height of a seat top. If the mass is 3 kgs and the height is 0.45 meters, what's the potential energy of the car at the top? Potential energy equals mgh. This gravitational potential energy is mgh. So 3 kilograms times 0.545 meters times the gravity. So we will get 13.5 joules. Force of 14.7 is used to drag that same cart, which was 3 kilograms, right? 3 kilograms. Along a distance of 0.9 meters, how much work is done at the cart. So now, work equals force times distance. Work equals 14.7 newtons times 0.9 meters. Lo and behold, 14.7 times 0.9, 13.23 joules. Interestingly enough, 13.5, 13.23, and actually if we did this with an actual 9.8, we'd end up even closer. The fact of the matter is, whether you go straight up or whether you go up a ramp, you end up using the same amount of energy, force times distance or MGH. And that's why ramps make things a lot easier, because you could be pulling up with more force to go straight up, or in the next problem, you could be pulling up with less force but going a longer distance. Kinetic energy of a 625 kilogram roller coaster that is moving at the speed of 18.3 meters per second. KE on a good day equals 1/2 mv squared. KE equals 1/2 625 times 18.3 squared. That will give us 0.5 times 625 times 18.3 squared. That's a big number. That's also a fun ride. 104,653.25 joules. Roller coaster, the above problem, we're moving at twice the speed. What would happen to kinetic energy? Well, now KE equals 1/2 mv squared. If we double this, we're going to square something that's doubled, so we'd actually get 4 times the KE. So because you're doubling the velocity, which gets squared, it's going to be a big, you'll see. So we had 104,653 joules from a velocity of 18.3. So let's see, our new velocity is 18.3 times 2. $36.6. So KE equals 1/2 m for 625 times 36.6 squared. 0.5 times 625 times 36.6 squared. That's going to give us 418,612.5 joules, which is 4 times as big as what it was before. So we're doubling a squared function, which makes it 4 times bigger. Conceptually and mathematically, you should know that for the final. Missy Dewater, 12,000 joules just before hitting the bucket. Missy's mass is 40 kgs. What's your speed? So we know KE equals 1/2 mv squared. 12,000 joules equals 1/2 m, which is 40, v squared. So let's do some math. 24,000 equals 40 v squared. 24,000 divided by 40. Take the square root of that. 24.5 meters per second. shit in the water about 50 miles an hour. All right. Conceptual physics time. Here we go. If I start with 100 joules, I have to keep 100 joules the whole time. So this is easy. At the ground, this guy is 0 joules. This guy is going to be 100, and that will be KE equals 1/2 mv squared. So 100 equals 1/2 m, which is 2. So there, v squared. So 1/2 of 2 is 1. Square root of 100 is going to be 10 meters per second. Coming here, if that's 50, that's got to be 50. And the v is 1/2 mv squared equals 50 joules. Half of 2 is 1. So v squared equals 50. So v is going to be about 7. Because I'm not going anywhere, that's still 50, which means that's still 50, and that's going to be 7 because it's the same. And then here 0, 100, and you'll see it's still 10. You guys did this, and we said don't worry about this, continue to not worry about that. I just don't know how to get rid of it. Use the law of conservation of energy to fill in the blanks. 1,000 kilogram roller coaster car. MGH is going to make this 45 meters. Velocity is 0. Here, 450 minus 200 is going to be 250,000 joules. Our H is going to be MGH, 20 meters. Our velocity, we're going to use this to do 1/2 mv squared. And our mass is 1,000. So 250,000 divided by, times 2 divided by 1,000. Because now, so multiply that by 2, both sides, then divide by the m. Now you can take the square root. It's going to be 22 meters per second. And then this guy, you're going to have no PE, which means this is going to be 450,000. Okay. Which means that's also equal to 1/2 mv squared, and we'll use that to get my velocity, just like we used this to get the velocity. 450,000 times 2 divided by 1,000. Take the square root. 30 meters per second. Next. Oh, we're almost done. Outstanding. Same basic deal. It's the same thing. Why did I use... I don't know why I put this in twice, kids. I don't know if it is in twice on yours. 450, 200, yeah, it's the same thing. Sorry. And okay, leaping far. Oh, we're done. 2 hours later. Determine leaping far, a mass of approximately 50 kilograms, has a speed at locations B, C, D, and E. Assume no friction. So at B, C, D, and E, all we care about are KEs. So at B, C, D, E, kinetic energy is 20,000 joules, equals 1/2 mv squared. C, 35,000 joules equals 1/2 mv squared. D, 20,000 joules is 1/2 mv squared. And E, 50,000 joules equals 1/2 mv squared. We know the mass is 50. So let's see how small I can write in here. 50, 50, 50, 50. So 20,000. We use one at a time. 20,000 times 2 divided by 50. Take the square root. So that one is going to be 28 meters per second. And actually, 20,000, 20,000 is going to be the same. 28 meters per second. 35,000 times 2 divided by 50 equals that. Square root of that. 37 meters per second. 5,000. Just kidding, 50,000. 50,000 times 2 divided by 50. That's our mass, and that's the algebra. The square root of it. 44 meters per second. Okay, team. I hope this was helpful. I am done 2 hours later. Sorry it took so long, but it's a big review packet for an entire year. Bring your review sheet, and definitely good luck studying on the final. Once you go through this, feel free to bring additional questions in on Monday. Please also don't forget to bring your books in on Monday. Alrighty, good luck. See you guys on Monday or during your final.